Hello everyone! In this video I'll be talking about binary arithmetics and logic operations, since we'll be using them all the time from now on in our codes. This video might be confusing if you've never learned this or coded a microcontroller, especially towards the end where I'll introduce signed and unsigned calculations using 2's complements. For some, these topics are simple, and for some they aren't. It depends on the person, but I'll say that these things are heavily logic-based and usually just click in place all at the same time, so if you don't understand, it's fine. You can keep watching and understanding the workings of computers and come back to this video in the future again, and hopefully it will click to you as well. So let's get started. First off, we'll start with the most basic elements that make the computers. I'm talking about logic gates. In the last video, I've said that a bit represents a value of 0 or 1. That 0 or 1 is the foundation that the computers are built upon. I'll explain that further in the video. The reason the computers work with zeros or ones is because they are made of transistors. And digitally, transistors only have two states, 0 or 1, which means on or off, or high voltage state or low voltage state. So inherently, computers have to use binary to make calculations, because of their innate structure. Those transistors are connected in a certain way to make logic gates, which are also further connected in a certain way to make more complex operations, which are also connected in a certain way too, and you get the idea. But the logic gates are where the literal logic first starts to form. They also have their corresponding bitwise operations that we'll be using in our code, but I'll talk about them more in a minute. Also, don't worry about why they are called gates. The reasoning seems more arbitrary than logical, so just accept it. Let's start with the most basic gate, buffer. This is the symbol for a buffer. I will denote A and B as my inputs, while Y will be our output. As you know, we are dealing with binary, so the only viable states for both inputs and outputs are 0 or 1. This gate just buffers the input, like its name suggests, meaning it just passes whatever its input is to its output. Let's construct the truth table of this gate. A truth table just means all possible combinations of input and outputs written on a table, which will let us see the gate's complete behavior. If the input is 1, the output is also 1, and if the input is 0, the output is also 0. Simple, right? There is also the opposite of the buffer, an inverter. This is the symbol for an inverter. As you can see, it's really similar to the buffer, with a tiny difference, a small circle on its output. The inverter, as the name suggests, just inverts this input and gives it on its output. Let's construct its truth table. If the input is 1, then the output is 0, and if the input is 0, then the output is 1. If you compare this table to the buffer, you'll see that its behavior is the exact opposite, meaning its outputs are opposite to that of the buffer. Next is AND gate. This is the symbol for an AND gate. Let's write the truth table first this time. It's called AND gate for a reason, because the only time its output is 1 is if both of the inputs are also 1, meaning if A and B are 1, then the output is 1, otherwise 0. Much like the buffer, all gates have their opposites. Opposite of an AND gate is called NAND gate. This is the symbol for a NAND gate. You'll see that the symbol changes similar to that of the buffer. It's the same as the AND gate, only there's a small circle on its output again. The small circle is commonly used to denote inversion, so you'll see it in other places as well. I'll construct this truth table first again. And as expected, it's just the AND gate with its outputs flipped. Both the symbol and truth table patterns will be the same for the rest of the gates as well, so I won't explain them anymore. One thing to note is that the NAND gate behaves the same as AND gate with its outputs inverted, right? So you can also connect an AND gate with an inverter in succession to get the same behavior. Next up is OR gate. Its symbol is like this, similar to AND gate, but it has a curvy input side instead. The truth table for the OR gate is like this. You'll see that what the gate does is the reason why it's called OR gate. If any of the inputs is 1, the output is also 1, meaning if A or B is 1, the output is 1, otherwise 0. The inverted version of the OR gate is called NOR gate, and like I said, it just has its output responses flipped, and its symbol just has a small circle on its output. The next gate is XOR gate. This is the symbol for the XOR gate. It's similar to OR gate, but it has another curved line on its input side. XOR stands for exclusive OR, and if you construct this truth table, you'll see why that is so. It's the same as the OR gate, except if both of the inputs are 1, the output is 0 instead. So the input A or the input B exclusively have to be 1 for the output to be 1. The opposite of XOR gate is called XNOR gate, and the symbol and truth table for it is like this. That's it with the gates. You may wonder the purposes of these gates, but they are all used for something or another, which is out of the scope of this video. Before ending this part, I want to show you how to construct some of these gates physically. For example, how do you actually make an AND gate? Here's an N-channel MOSFET and here's a P-channel MOSFET. I will assume you know what these are since explaining them would take a whole nother video. Don't forget, 1 means high voltage and 0 means low voltage on the physical level. In real life, because of the nature of the MOSFETs, the shortest way to make the gates will always lead to an inverted output, which will get inverted again. Making an AND gate actually requires making a NAND gate and inverting its output after. Here's what I mean. This is how you construct an AND gate, you would think. But let's look at the truth table of the circuit. As you can see, this is not an AND gate, it's a NAND gate. To get an AND gate from this, you can use this circuit, which is how you make an inverter. And no, you can't make a simpler AND gate than this. The reason for this is, take a P-channel MOSFET for example. Because of its nature, you can only connect it to the high side, like this. When you apply 1 to this MOSFET, the output goes to 0. And if you apply 0 to this MOSFET, the output goes to 1. Note that the resistor is only here to stop a short between the supplies. Take a look at the same circuit arrangement for an N-channel MOSFET. Because of the nature of the N-channel MOSFET, you can only connect it to low side. If you apply 1 to this MOSFET, the output goes to 0. And if you apply 0 to the MOSFET, the output goes to 1. In both cases, the MOSFET will act like an inverter, so by nature, the MOSFETs are always inverting. Now let's be clear, you can connect an N-channel MOSFET to high side, and this would normally fix this inverting problem. But you will have to deal with more than a couple volts of voltage drop across the MOSFET because of the required VGS voltage for the MOSFET to turn on, which will only increase as you draw more current from the output, and this will render this circuit useless. The same also goes for the P-channel MOSFET. That's why I said you can only connect an N-channel to low side and P-channel to high side. You can connect them otherwise, and you can look up the term MOSFET bootstrapping for an example of that, but in a digital circuit like this, that will not be possible. Because the MOSFETs are inherently inverting like this, in real life you can't make a gate without making its inverse first. So in some datasheet schematics like this, you'll see that the AND operation is done by inverting an output of a NAND gate. This is not a redundant, weird typo. On the physical level, this is how it's done, though most of the time the datasheets will hide this fact. Let's see the OR gate as well. This is how you make the NOR gate. You can again put an inverter to its output to turn this into an OR gate. Now, if any of the MOSFETs are 1, the output is 1, otherwise it's 0. You can look at how to make the other gates by googling them. I won't spend any more time showing them here. A simple Google search will yield schematics for all of the gates you want. Let's talk about how binary representation works before we get into bitwise operations. Like I said, binary numbers consist of zeros or ones. But how does this representation work? For the sake of simplicity, we'll only consider 4-bit numbers throughout the video, but know that anything I show here will apply the same for any bit length numbers. Take this number for example. This number represents the number 13. How do we know that this number actually represents 13? Well, this is how you find it. Every bit has their weight values. From the first digit to the last digit, this value starts from 1 and increases by times 2 each digit, like this. To find what number this binary value represents, we can do the following operation. Multiply each bit with their corresponding weight, and add them up, like this, and you get 13. You may ask, where does this operation come from? Why are we multiplying with weights? What are weights? The answer is modular arithmetic. You actually perform this exact operation whenever you talk about numbers. Let me show you what I mean. Take a normal number we use every day, like 1725, which I'll refer to as decimal numbers from now on. How do you know that this number represents 1725? You do the exact operation as before, but this time the weight will increase by times 10. The reason for why the decimal number weights increase by times 10 is because we use base 10 in our daily lives. You should have learned about mod arithmetics, at least its basics, but if you don't know or remember, you can look them up, since they are very important concepts for computers. But to simplify, you can consider this. Base 10 is called base 10 because we have numbers from 0 to 9. So we can represent numbers from 0 to 9, but when we increment beyond that, meaning if we consider for example 10, we wrap the first digit back to 0 and increment the next digit. This is why the second digit has the weight of 10, hence we are using base 10 representation. The binary representation is the same. It only has two numbers to represent, 0 or 1. Meaning, if we increment to 2, the current digit wraps around to 0 and increments the next digit. Hence it is base 2, and the weights increase by times 2. Before going any further, I want to show you how to turn a decimal value into binary. Say for example you have the number 11. How do you turn this number into binary? The easiest way is to sequentially go over the binary weights, starting from the highest weight. Is there an 8 inside of 11? The answer is yes, so put 1 in place of the weight 8 and subtract 8 from 11. Now we keep going. Is there 4 inside of 3? The answer is no, so put 0 in place of the weight 4 and move on. Is there a 2 inside of 3? The answer is yes, so put a 1 in place of the weight 2, subtract 2 from 3 and move on. Now is there 1 inside of 1? The answer is yes. And we're done. One thing to note is that if your highest weight times 2 is equal or bigger than your decimal number, you need more bits to be able to represent this value. Here's what I mean. Consider the number 18. 2 times 8 is equal to 16. So we can only represent numbers that are 15 or lower using 4 bits. And you'll see that we will be off by 3. But if we use another bit, as you can see, now it is representable. If you want to find the maximum value you can represent for given amount of bits, use the formula 2 to the power of n minus 1, where n is the number of bits. And that's it for the binary basics. Let's talk about basic binary arithmetics. Let's see how we can add and subtract in binary. Consider these two numbers, 5 and 3. If we added these numbers together, we would get 8, right? Let's do this addition with binary as well. 1 plus 1 is equal to 2. But that causes a carryout and wraps around since binary is a base 2 representation. Next digit. 1 plus 1 plus 0 is equal to 2. And again. Now we only have 1, so it's 1. Is this 8? From the weights, you know that this is 8, so the answer is correct. And of course it is, since this is the same math as you always use in your daily life, just with base 2. And you can try other examples, they will always work out. Let's talk about subtraction. Binary subtraction is also the same as decimal subtraction, as you would expect. But let's not get into negative numbers yet. That is the topic of the next part of this video. For now, we'll only use positive numbers. Let's consider the number 13 and 7. If we subtract 7 from 13, we would expect the result to be 6. Let's go ahead and do this binary calculation. 1 minus 1 is equal to 0. Next digit. 0 minus 1 is negative, so we need to see if we can borrow from the next digits. And yes, we can. But before that, let's look at a decimal example. 256 minus 94. Let's calculate this to understand what we are actually doing. You go digit by digit, right? You start from 6 minus 4, which is 2. Okay, the next digit. 5 minus 9 is a negative number, so we look for a borrow. And it exists. What are we doing when we borrow? We are subtracting 1 in the borrowed digit, right? Then that digit ends up adding 10 to our current digit, right? Why is that? Why are we adding 10? It's because we are using base 10, meaning for each digit, weight increases by times 10. 1 in the second digit is worth 10, and 1 in the third digit is worth 100, right? Meaning, the worth of each digit is 10 times higher than the digit before it. That's why the 1 we borrow from the next digit is worth 10 in the current digit. So, 10 plus 5 minus 9 is equal to 6, and minus 1 plus 2 is equal to 1. Let's go back to our binary example. Because we are using base 2 in binary, the borrow we take from the next digit will be worth 2. I know there is no 2 in binary, but there is also no 10 in base 10. This is just how the math works. If you are taking a borrow, that means the result of this digit was a minus value. So there will never be 2 on this digit, since that minus value will be added to it. 2 minus 1 is equal to 1. Next digit. Minus 1 plus 1 minus 1 is also a negative number, so we borrow from the next digit. 2 minus 1 plus 1 minus 1 is equal to 1. And the next digit is minus 1 plus 1, which is equal to 0. And indeed, this binary value is 6. You can also do this with other numbers and it will always work out, since it's the same as the decimal numbers we use in our daily lives. How about multiplication and division? Well, technically, multiplication and division are just a sequential addition and subtraction by nature. In fact, computers don't multiply or divide. Actually, computers don't even do subtraction, they only do addition. And addition is actually enough to do all math operations. I'll get into that in a little bit in the next part of this video. Let's see how we do multiplication. Look at this term, 5 times 3. You know it's 15, but you also know that the actual calculation is 5 plus 5 plus 5, right? Well, the same goes for binary as well. Take the same 5 in binary, add it 3 times over, and you get 15. Division is a tiny bit more complex, but the same logic applies. Let's consider the numbers 15 and 4. If you divide 15 by 4, you would get 3 as a quotient and another 3 as the remainder. But how do you do this operation with addition or subtraction? What you actually do when you are dividing is that you are subtracting the divisor from the dividend until the remainder is less than the divisor. Let's apply this to our example. Subtract the divisor from the dividend, and every time we do this, we add 1 to our quotient. This is because every time we were able to do this subtraction, there were one more divisor inside of the dividend that we subtracted. Now, is the divisor bigger than the remainder? If it was, we would finish this calculation, but it isn't. Now, take your remainder and subtract the divisor again. Add 1 to your quotient. Check if the divisor is bigger than the remainder again. It's not, so we continue. Take the remainder again and subtract the divisor. Add 1 to your quotient. Is the divisor bigger than the remainder? This time the answer is yes, so we are done. And the last remainder is our final remainder. Let's do this with our binary equivalent numbers. And as you can see, the math checks out. Now, this isn't how computers actually do division. They use another algorithm to accomplish this task. But this shows you the idea that multiplication and division are just glorified addition and subtraction. And that's it for the basic binary arithmetics. Let's talk about bitwise operations. These are operations we'll use in our codes that allow us to manipulate bits directly in our computer instead of relying on arithmetics. And you'll see why this is important when we start coding, especially for microcontrollers. Because logic gates represent the physical logic circuitry that are inside of the computers, and they offer convenient manipulations, they have their respective bitwise operations as well. But there are a couple more bitwise operations that also have their physical corresponding circuitry, of course, but don't necessarily have a logical meaning. Let's start with the AND operation. The symbol used in C language for AND operation is ampersand. You already know how AND operation works from the previous part of this video, but how does it work with binary numbers as an operation? Here's the truth table for AND operation. Take these two numbers for example, 10 and 12. But let me tell you that in bitwise operations, as the name suggests, you don't look at the whole number, you look at the bits. Meaning, what this value represents doesn't actually matter. You don't care that this is 10 or 12. We are looking at manipulating each bit, hence these are called bitwise operations. This is a very important concept for microcontrollers, and explaining it on the spot would be difficult if you never coded a microcontroller. The best way to understand is to keep watching. You'll quickly understand the importance of bit manipulation in the upcoming videos. Let's go ahead and perform this operation. We'll do this operation like we've done in the arithmetics video. 0 and 0 gives 0. 1 and 0 gives 0. 0 and 1 gives 0. 1 and 1 gives 1. Before anything, let me inform you that setting a bit means turning that bit into 1, and clearing a bit means turning that bit into 0. You may ask, what is the purpose of this operation? The AND operation is used to clear the target bits. Check this truth table. Let's assume that one of the inputs is unknown, which I'll denote as x. You know that if you AND an unknown value with 1, the result will be 1 if the value is 1, and 0 if the value is 0. Meaning the result will be whatever the x is. And you also know that if one of the inputs is 0, the result of AND will also be 0 no matter what. So you see, if you AND something with a value, any place you put 0 to will be cleared, while any place you put 1 is unaltered. That is why AND operation is used to clear the target bit. Let's see this example. Let's say that I want to clear this number's 3rd, 4th, and 5th bits, and leave the rest of the number untouched. You can just put this number in an AND operation with the numbers that has 0 on the bits you want to clear and 1 on the bits you want untouched. And there you have it. Next up is OR operation. The symbol for OR operation in C language is a vertical bar. OR operation is the exact opposite of the AND operation. You use OR operation to set a target bit. Let's look at this truth table. Let's do the same truth table with one of the bits unknown like before. You know that if you OR an unknown value with 1, the answer will be 1 no matter what. And if you OR an unknown value with 0, the result will be 1 if the x is 1, and 0 if the x is 0. So the result is whatever the x is. That is why OR operation is used to set a target bit. Let's see this example. Say that you want to set the 4th, 5th, and 6th bits of this number and leave the rest untouched. You can just OR this number with a number that has 1 in places you want to set and 0 on the places you want unchanged. There you have it. Next up is XOR operation. The result of an XOR operation is interesting and usually forgotten, but it is important. The symbol used for XOR operation in C language is caret. XOR operation is used to flip a target bit. Let's look at its truth table. Let's do the same truth table with one of its bits unknown like before. If you XOR an unknown value with 1, the result will be 0 if the value is 1, and 1 if the value is 0, meaning the result will be the opposite of the x, which I'll denote as x with an apostrophe, which is also called x naught. And if you XOR the unknown value with 0, the result will be 1 if the value is 1, and 0 if the value is 0, meaning the result is the same as x. Now you see where the flipping bits is coming from. Let's see this example. Let's say you want to flip the first 3 bits and the last bit of this number while leaving the rest untouched. You can just put this number in an XOR operation with the number that has 1 on the bits you want to flip and 0 on the bits you want untouched. And there you have it. Note that this operation does the job of an inverter as well, since it essentially inverts the bits you choose. You may think that we're done since this covers all of the gates, but there are actually 2 more bitwise operations. Let's talk about shift operation. There is no truth table for shift operation since it is not logic based. As the name suggests, the numbers are either shifted to the left or right. That is why it has 2 symbols in C language, 2 less than symbols for shifting left and 2 bigger than symbols for shifting right. All this operation does is shift the numbers. Even though it may seem unnecessary, it is a very important operation that you will constantly use. Let's see the example first. Let's shift this number to the left 2 times. And everything I'm going to say will apply to right shifting as well. The rightmost number won't be left empty, of course. It will usually default to 0. Let's do this operation again. There you have it. Simple, right? Even though this operation alone is very important already, there is one more thing to note here that is very important. This operation has an important mathematical meaning. Consider this decimal number 5. What happens when you perform the same shifting operation on this number? You can see that the resulting number is multiplied by 10 each time. Try it for another number. You see, it still applies. This is again because we use base 10 in decimal numbers. So can you guess what happens when you shift a binary number? That's right, the result will be multiplied by 2. Check the weights of the binary numbers to calculate their decimal equivalent. And as you can see, the result increased by times 2 each time. This concept is more important than you might think, but I'll just leave it at that. Before the next operation, I want to add something. In computers, you don't have infinite bits to store numbers. You have physical transistors that store them. So any bit beyond that physical limit will simply be truncated. So when you shift this value to the leftmost number will be lost because there physically exists no transistors to store it. That also means that this multiplication by 2 doesn't work if the resulting number is bigger than what you can store using your bit count. Last bitwise operation is called ones complement, and we'll talk about it more in the next part of this video. Its symbol in C language is tilde. Ones complement just means to flip every bit in the number. So take this for example. To get the ones complement of this term, simply flip every bit. And there you have it. When you think about it, this operation is the same as XOR operation. And if you simply XOR this number with only ones, you would get the same result, right? This operation also has a mathematical meaning, even though it's not always used for that. If you add a number and its ones complement, you'll always get the highest number storable by your bits. You know how to find that from the previous part of this video. 2 to the power of 8 minus 1, which will be 255. And this makes sense, right? With adding ones complement, you always add 1 to wherever is 0, and 0 to wherever is 1. And the result will always end up with 1s, which is the highest storable value. And that is it for the bitwise operations. This is the end for the first part of this video. I divided this video into 2 parts since it was getting too long. In the next part, I'll explain how negative numbers work along with some extra info. If you liked the video, you can always leave a like and subscribe. It's always appreciated. And I'll see you in the next video.